Okay.
All right, there's 5 people already there.
Okay. Hello.
Cool, thanks a lot, Clement.
Hello.
Hello, Thomas.
Hello.
How are you?
I'm very good. And you?
Okay, I'm fine. We're not. Okay, I'm sorry there was a misunderstanding on the time zone.
It's fine. It's good I checked. I always check these things because I doing time zone calculations is too much maths for me. I have to.
It is. Yeah, I feel the same. I feel the same. Will you be sharing your screen or a tablet or something?
I'll just do PDF slides. Do you want me to check that now, see if it works?
Sure. Yep, perfect. Just go to...
And you should be able to see them full screen now. Yep, okay, cool.
And so the way the colloquium generally works, I think we mentioned it during our email discussion, but generally we have some undergraduate students joining us as well.
Yeah.
And so we can have all range of questions from experts to very basics. And generally it's pretty laid off. So if people have questions, they generally we encourage them to interrupt you, if that's okay with you.
No, that's perfect. I prefer it that way.
And the colloquium is also live on YouTube, but I will be monitoring the chat on YouTube and ask you if any question are asked there. You don't have to, you don't have to worry about that.
Sounds good.
I look at it regularly. And so I don't think I told you, it was actually Thomas Saylor that recommended that we invite you. Yeah,
no, you did tell me this because I gave a talk in Lippen, like in November, I think.
Okay, well, I think he really liked it because he strongly recommended that we invite you. Was it the same talk or was it a different one?
Yeah, this is going to be it's going to be the same talk.
Okay.
Yeah, I've known Thomas for a while since we did our first postdoc together in Paris. So we were office mates for some time.
Oh, okay, I didn't know that.
Yeah.
Okay. Excellent.
Try and turn my desk around so that there's some light.
Yeah, I'm fortunate enough to still be able to work from my office. When is the last time you saw your office? Do you get a chance to still go there every now and then?
I have been in my office precisely once because when I started at Bath, it was the middle of lockdown. I only started in May last year. So I went once to see that it existed. And this is the only time I've ever been.
Ah, sorry.
It's fine. Working from home is, I got used to it quite quickly. So
okay.
It's not
okay,
so
but I think when you arrive to a new place, getting a sense of collegiality, of getting to know your colleagues is a bit hard.
I miss this a lot. And also you have so many questions which you would normally ask at lunchtime.
Sure, yeah, you just knock on the door next, yeah,
exactly.
You just go next door and just, yeah.
And an email seems like so much effort and it always feels like you're annoying people when you email them. So yeah, this is a pity.
Yes.
And what's the general situation where you are? Is everything open or closed or?
So in the US, at least in Georgia, the politics is let people sort it out. So the governor took very minimalist measures. He went to the point of actually forbidding cities to have a mask mandate.
Right.
Like he actually sued Atlanta because they say masks should be mandatory, and like he actually tried to forbid that. So that was a bit of a weird situation.
Right.
And so it's really up to you pretty much. So some people are extremely cautious, some people are not cautious at all. We have a wide range of situations. Generally, I mean, and it goes all the way to restaurants. Some are like closed, maybe not forever, but I don't think they know when they'll be reopened. Some are fully open, some do only what they call curbside or like pickups. You really have all kinds of situations. The campus is fairly empty though. Like you barely see any student. There are some classes taking place in person, but the students just come, go to their class and then go back home or to their car or whatever, but they don't really hang out on campus anymore.
Yeah, we've been teaching online completely.
Okay.
So that's another strange thing, just giving a lecture to 200 people who have their cameras turned off and they interact in the chat. They ask questions in the Zoom chat. And so you're talking to the chat basically.
Yeah. Well. Okay, hopefully there will be a bit more interactions here today during your classes. Okay, so what do you teach right now?
So last semester I was teaching basically automata theory. So the standard material on automata theory that everyone in computer science learns in like first or second year.
Okay.
And Turing machines and things like that.
Okay.
Yeah.
So, okay. I'm always curious to know if people teach two ways automata. Do you mention two ways automata? You know, automata that can go both ways.
I think we had a question on this. We didn't teach it as standard, but I think we had one of the more difficult questions was exploring this automaton.
Okay. Yeah, I'm always curious. Somehow there's always left out, but I kind of like them for some reason. I'm not sure why. Anyway, okay, let me introduce you and then the floor will be all yours. So welcome everybody. Today we have the pleasure of welcoming Thomas Powell, who is an assistant professor in Bath in UK. And you may know him from his proof theory blog that he edits with Anupam Das, which I strongly recommend visiting if you get a chance. There's all kind of research and open discussion on proof theory that I think was extremely interesting. And today we'll be giving a talk on quantitative Tauberian theorem. Thank you, Thomas.
Thank you. All right, so my talk is in two halves, and I have nothing against the first half taking up the entirety of the talk, so there's no obligation for me to get to the second half. If there are enough questions in the first half, that's absolutely fine by me. So I thought this would be quite well suited to the brief because it starts with a short introduction to applied proof theory, and then I'm going to outline something that I've been working on recently. So hopefully the two will work well together. But if there are lots of questions, I'd love to just stick on part one and go through things in detail and answer general questions about the area. So it's entirely up to you. Okay, so this is a 30-minute introduction. Normally that's how long it takes, but it can be longer. So if anyone sees a talk on applied proof theory, there's this famous quote due to Georg Kreisel, which is always appears somewhere. It also appears in many of the papers in this area. And it's quite cryptic, but it's somehow the unofficial quote for this area. So what more do we know when we know that a theorem can be proved by limited means than if we merely know that it is true? So what Kreisel was getting at here is that the proof of a theorem gives us more information than just the truth of that theorem, okay? So it's one thing to know that a statement is true, but the proof, of course, tells us why it's true and also gives us a lot more information. And so applied proof theory is a branch of logic that uses techniques from proof theory to exploit this phenomenon, that the proof tells you more than just the truth of the theorem, and it tries to make precise how you can get stuff from the proof of the theorem to make the theorem stronger. Okay, so in one line, that's what applied proof theory is after, is analyzing the proof and using techniques to get more stuff from the proof. So more stuff than the simple truth of the theorem. So I'm going to give you a simple example and a more complicated example. So the simple example, and what I want to convey here is that basically everyone does applied proof theory. It's not an unusual thing. So typical question might be, give me an upper bound on the nth prime number. Okay, and you'd get a pen and paper and you think, well, what is that? So one way of thinking would be, well, what is the nth prime number? How do I know it exists? So there's a classic proof from Euclid that says that there are infinitely many primes. So specifically, if I have the first n minus 1 primes, I can multiply them together and add 1. And I know that this new number has a new prime factor that can't be any of the first n minus 1 prime numbers. And so I know that there exists a next prime number, so to speak, and that prime number is bounded by n. Okay, so I've got two things. I've got the next prime number, but I've also got a bound on how far I need to look for that next prime number. So in other words, we can turn this argument into a recursive inequality. And a simple induction will prove that the nth prime number is less than 2 to the 2 to the n. Okay, this is not an efficient bound, but it's a crude bound that you get from the classic ancient proof that there are infinitely many prime numbers. And this is a very simple example of applied proof theory in action. Okay, there's no logic here. There's no kind of proof theory proper. It's just looking at a proof, looking at it a bit more carefully than you normally would, and trying to work out, kind of basically get an algorithm from the proof. Okay, so the classic theorem says there are infinitely many prime numbers, or that the nth prime number exists for all n. And actually what the proof does is more, it gives us a crude bound on how far we need to look. So that's a simple example of applied proof theory, or the kind of reasoning that we do. But a much more complicated example is the following. So this is a famous theorem of Littlewood, and he's looking at the classic number theoretic functions. And I won't go into detail on what this theorem means. That's not important. But the gist of the theorem is that these two functions change signs infinitely often. Okay, so I think it starts off negative and then it turns positive and backwards and forwards. And the proof that this happens is completely non-constructive. Okay, so it uses a case distinction on the Riemann hypothesis. So if the Riemann hypothesis is true, then we can get the theorem. If the Riemann hypothesis is false, then we can prove the theorem. But we don't know which of those is true, right? So it's a really non-constructive proof. And at the time, there was no numerical value of x for which pi of x being greater than li of x was known. All right. So basically, we know that this is going to happen at some point. In fact, we know it's going to change backwards and forwards infinitely often. But at the time, nobody knew when that happened for the first time. All right. So this is an example of a really non-constructive proof that says that something is going to happen, something exists, but we have no idea how to find it. And In the 1950s, Kreisel, who was one of the first proof theorists to put forward this way of thinking about proofs, basically extracted recursive bounds for the sign changes. So he did what I did on the previous slide, but to a much more complicated proof. And he gave much more complicated recursive functions which tell you how far you need to look until you find the next sign change, all right? And there's a revealing paragraph which I've sort of copied and pasted from this paper. You don't need to understand it in detail, but I'm going to come back to one key thing he says. So the difficult direction is apparently when the Riemann hypothesis is true. And then it's difficult to know what these bounds are. So if the conclusion holds when the Riemann hypothesis is true, it should also hold when the Riemann hypothesis is nearly true. Okay, so not all the zeros need to lie on the line, but near it. Okay, so this is quite a cryptic statement, and I'm going to try and make more precise what Kreisel was doing here later. But the basic idea is that applied proof theory, it's a completely natural thing to look at a proof and try and get more information from it, but it can be done in a really powerful way using proper proof theoretic techniques to produce very subtle things. So bounds which didn't exist before, and for which there was, like, looking at the proof, it was not obvious at all what those bounds would be. Okay, so I've given you a simple example and a very complicated example, and now I'm going to give you a modern example. Sorry, Clement, did you have a question?
Yeah, so can you go back to the previous one?
Sure.
So what you're also saying is that he was able to weaken one of the hypotheses slightly.
Exactly.
And was that known at the time, or was that a discovery? Like, was it known that if you take a slightly weaker Riemann hypothesis, the result still holds?
I don't think it was. I don't think this is something that people would necessarily have recognized as being important. Okay. But you're absolutely right that in doing this, it's also a stronger result. You're weakening the hypothesis, right? Mm-hmm. So okay. Yeah, absolutely.
Thank you.
So here's a modern example, and it's picked from one of my papers, but it could be any number of papers in this area. So I was looking at fixed point theory, and again, you don't need to understand the details. I'm just trying to show you the shape of the theorem. So this is a proof in fixed point theory. So we've got a Banach space, a mapping, and the interior of the fixed point set is not empty. And it can be shown that the sequence of iterates converge to a fixed point of t if those conditions are satisfied. And so I looked at the proofs, and I tried to extract some quantitative versions of these theorems. And there are a number of quantitative things that you get out of this. And one theorem, so I've given basically one of the most concrete corollaries in this paper, which doesn't look like proof theory at all, right? So this is just a non-expansive mapping in an LP space, and it tells you how far you need to look before your approximation to the fixed point is kind of epsilon close to a fixed point. So it's how far do you need to look before you've got a good approximation to the fixed point. And by analyzing these proofs in detail, which are non-constructive, you can give a very concrete sort of rate of, this is the technical term is a rate of asymptotic regularity, but this is a concrete function which tells you basically how far you need to look so that you've got a good approximation. And many results in modern applied proof theory are like this. So this theorem doesn't look like it's something that you would see in a proof theory paper. And actually most of these papers, including this one, are published in journals in the area of application rather than in logic. But there are proof theoretic ideas at play here that allow proof theorists to kind of pretend to be mathematicians and pretend to do useful things. And secretly, we're just using proof theoretic methods to get these numerical results. So how does proof theory work? So what parts of proof theory come into play here? So we got this bound on the nth prime number without any special techniques at all, just by looking at the proof. But in order to be useful, serious applications usually involve something non-trivial, okay? So here are some of the things that they involve. Proof interpretations, particularly Gödel's dialectica interpretation. The dialectica interpretation originated as a technique for proving the consistency of piano arithmetic. And it's no coincidence that this is now being used to extract programs from proofs, because the idea behind the relative consistency proofs was that we want to reduce the consistency of a complicated theory to a simple theory. Okay, so in this case, it goes from arithmetic to a simple lambda calculus. And the idea is that if you can prove an inconsistency in the big theory, then an inconsistency also exists in the small theory. So you can reduce it to a simpler thing. But the same technique allows you to actually take a proof in a complicated theory and get some kind of program out of it. So many techniques that were originally invented to establish consistency at the beginning of the beginning and mid 20th century are now being repurposed to, in a more positive way, to produce programs from proofs, or to produce bounds from proofs of convergence, etc. Okay. Another thing that's important is computability and complexity in higher types. Typically what you get is you get some complex recursive functional from analyzing the proof, and often you need to simplify this in some way in order to get something meaningful out. Logical relations play an important role. So there's one very important logical relation called majorizability, which is a generalization of the ordinary inequality on natural numbers to higher types. And this technique allows you to deal with proofs involving compactness, for example. And of course, formal systems and type theory are important, because one of the things you want to do in applied proof theory, once you've found a number of case studies in an area, once you've looked at a number of proofs, you've applied your tools to get something useful out of it, like a rate of convergence or something else, you want to try to understand what's going on a more abstract level. It could be that you've analyzed a lot of related proofs, and either you've met the same obstacle in those proofs, or you've been successful for a similar reason. And you want to formalize this and explain why that was generally possible. And so for this, one often needs to devise special formal systems that allow one to reason about kind of real mathematical proofs. So, and typically these involve abstract types for representing abstract spaces, so an abstract Banach space or something like that, or an abstract metric space. And so formal systems and type theory are very important in this area when it comes to explaining why certain phenomena appear. So why are the techniques from applied proof theory successful for this kind of proof? Okay, and typically one also needs to do some serious maths as well. So this is, applied proof theory is kind of the interplay of proof theoretic techniques and mathematical intuition. You can't apply these proof theoretic techniques blind. In theory, you could formalize a proof in a theorem prover, and you could press a button and you could get a long, complicated lambda expression out of it. But that wouldn't necessarily give you anything useful. It could be massively inefficient. It could be that the actual rate of convergence is hidden in there somewhere and you have to stare at it until you get it out. So really you need to use your own mathematical intuition in conjunction with these techniques to achieve something useful. So what can we achieve with applied proof theory? So the first thing is computational information from proofs, and that's something that I've exemplified in these initial illustrations. So proofs which at first glance are non-constructive can be analyzed to obtain some kind of computational content, a rate of convergence, a point at which a function changes sign, a bound on the next prime number, all examples of computational information, so a computational analog of the theorem that had been proved. And in the rest of this introduction, I want to talk about other things that we also get with applied proof theory, which are a bit more subtle. Sorry, I can't see my clock here. How long have I taken already? So I can kind of pace myself.
You're at 15 minutes.
15 minutes, okay, good. So I'm going to take a little segue now, go into look at something slightly different, but then I'm going to converge back on the ideas before and using sort of approximate versions of things like the Riemann hypothesis, or approximate versions of lemmas and proofs. So there's a really nice blog post by Terence Tao in 2007, which is called Soft Analysis, Hard Analysis, and the Finite Convergence Principle. And I really recommend this to anyone who's interested in analysis or proof theory. It's a really, really lovely essay, and it focuses on something really important, which is very relevant for what we do in applied proof theory. So I've taken some quotes from this essay, and the emphasis is mine. So this essay, it is about the connection between hard and soft analysis. So soft analysis is kind of, in a sense, non-computational analysis, and hard analysis is more quantitative analysis. And it's about the connection between these two forms of analysis. And I remember when I was a master's student, I looked at some of the proofs in arithmetic combinatorics. This was the course I took, and it was about proofs that there are infinite arithmetic progressions of primes. And these proofs use a lot of analytic techniques. And one thing that struck me as being very elegant at the time was they used a kind of finitary Fourier analysis to do something. And so I'd already encountered this kind of finitary thinking as a mathematician before I became a logician. And this essay was great because it connected what I knew as a mathematician to what I was doing as a proof theorist. And so the idea is, so one of the things that Terence Tao looks at in this, he gives several examples of this correspondence between hard and soft analysis, and I'm gonna put some of those on the slide in a second. He gives a finitary analog of a really simple result, that every bounded monotone sequence converges. So this is something that you know from first year analysis. He shows that it's not obvious what the finitary version of that should be. And then he talks about why this kind of finitary version of analytic principles of kind of simple infinitary principles are important. So I'm going to start by looking at an even more trivial infinitary statement. So this isn't in the essay. This is something much, much simpler. It's not to do with analysis or anything. It's just simple predicate logic. And it's called the drinker's paradox. So the way this is normally formulated is that in any pub, there is someone such as if they are drinking, then everyone is drinking. So it's not really a paradox. It's confusing because it uses classical logic in the proof, and so it makes you think that everyone is drinking because this person is drinking. So you can write this statement in simple predicate logic as follows, and the proof is very simple. Either everyone is drinking, and so we just pick X to be some canonical drinker, okay, because they're drinking and everyone is drinking, so the statement must be true. Or there is at least one person who's not drinking. And if there's one person that's not drinking, we can pick them to be this canonical drinker, because it's not the case that they are drinking. And so from that, we can prove anything, okay? So it's to prove this statement, you do a simple case distinction. It's a simple argument in classical predicate logic, but it's infinitary in the sense that it's computationally problematic. So there's no effective way of finding this drinker, okay? We'd have to go through infinitely many drinkers to work out whether or not there is somebody that's not drinking, okay? So it's a very simple statement, but it's got a classical proof and it's computationally problematic, okay? So I'm gonna characterize this as being an infinitary theorem for that reason. It's not finitary because we can't grasp it computationally, all right? So let's finitize it. And what I'm going to do here is I'm going to carry out a series of simple logical equivalences. And the result is going to be a reformulation of this drinker's paradox, which is completely equivalent to the original version, but somehow computationally manageable. All right. So the original statement of the drinker's paradox, if I move my mouse around, can you see that? Yep, okay, good. So the original statement is that, well, there exists a drinker such that if they're drinking, then everyone is drinking. So what I'm going to do is I'm going to pull this quantifier out of the front. You can do that. And then I'm going to put two double negations. So I'm going to put a double negation in front of this. So this statement is equivalent to not this statement, okay? Not A is equivalent to A in classical logic, but fine. And then what I'm going to do is, remember, if I have a not in front of a quantifier, the exists flips to a for all flips to an exists. So I'm going to take this single negation here and I'm going to bring it to the inside of the formula. So what I end up with is it's not the case that for all drinkers, there exists another drinker such that it's not the case that this thing holds. All right, so I've just taken one negation and I brought it inside the quantifiers. And what I'm going to do now is, this is a for all exists formula. So I'm going to take this exists out as a function. So it's not the case that there exists a function such that for all drinkers, not this happens. And now this y has been replaced by an f of x. And finally, I'm going to bring this last negation inside. And the final result is the following. And then I'm going to get rid of the double negation on the inside of the formula. So it's a series of simple logical equivalences. And the result is that for all f, there exists an x such that if that person drinks, then drinker f of x is drinking, okay? And we can solve this computationally. Either f of x is drinking, and then we just set x to be c for some, oh, sorry, I think this x should be a c here. So this f of x, this is f of c, and that's f of c as well. So we see if f of c is drinking for some generic person in this pub. If f of c is drinking, then we just set x to be c, and if f of c is not drinking, we set x to be f of c. So we can reformulate this into words. In any pub, there's a person such that if they are drinking, then everyone is drinking. The finitary version of this is, given a pub and any function f, there is a person in c and f of c such that if they are drinking, then person f of x is drinking. So what we've done is, the computational problem with the original drinkers paradox was that if, then everyone is drinking, because the everyone, we have to check everyone to make sure that our guess is right. But by replacing this with a function and bringing it out, we only need to check two things. Okay, so we've reformulated the drinkers paradox in a finitary way, and finitary means we can actually find a drinker, we can find a witness for this formula here. It's completely equivalent, and this process of finitization corresponds to the classical dialectical interpretation. So in other words, it corresponds to one of these proof theoretic techniques that we use in applied proof theory. Okay, so this thing here looks very logical, right? So even if you've never heard of these proof interpretations, that's fine. What I want to show you here is that we can take an infinitary theorem, we can do a bunch of logical steps, and we can arrive at an equivalent but finitary version of that theorem. And it turns out we can do this fairly systematically to formulae of much bigger complexity and formulae in a much richer language. Okay, so formally with lots of quantifiers and potentially in arithmetic or analysis. And now I'm going to give you, having looked at this very simple logical example, I'm going to give you the example that, well, a formulation of the example that Terence Tao looks at in this essay. So this is the monotone convergence principle. We've got an increasing sequence bounded above that say it's an increasing sequence in 0, 1. Then that sequence converges, or another way of saying that is that sequence is Cauchy. So for any epsilon, there exists an n such that the sequence is within epsilon of each other from that point onwards. All right, so it's a simple principle of analysis, but it's infinitary because in general, we can't find the point n in epsilon. And there are examples of these called Specker sequences, which basically encode Turing machines. They encode the halting problem in a sequence of rational numbers. And from that, you can show that you can never find kind of a rate of convergence. You can never find a program which in epsilon gives you an n. But if we apply the same kind of logical manipulations to this formula, to this theorem, we end up with a finite convergence principle. And this looks like what we had on the previous slide. We take an epsilon and an f, and we say, well, there's an m sufficiently large, depending on the epsilon and f, such that we can find in this finite sequence a interval where the elements of the sequence are within epsilon of each other, but only a finite interval. And the fact that we're looking at all possible finite intervals in some way means that this finite convergence principle is equivalent to the original monotone convergence principle. But unlike the monotone convergence principle, we can always find a point. We can always find this interval, all right? And more precisely, by looking at the original proof of the monotone convergence principle, we can extract a bound on how far we need to look before we find a suitable interval. Okay, so this is, I've written this in a slightly different way to how it is in the essay, but what I wanted to show here is that there are there's a natural mathematical theorem that everybody knows from first year analysis, and we can give a slightly weird looking finitary formulation of that. And that matches up to some fairly simple logical reasoning we were doing on the previous slide. And what I wanted to get across here is that the route from the monotone convergence principle to the finite convergence principle can also be done systematically using logical ideas. So again, I shouldn't have put this big block of text on this, sorry, but I've underlined another snippet from this essay. So can we actually use this finite convergence principle for some non-trivial finitary application? And the answer is a definite yes. And so Tao goes on to talk about how this is used. So what we're interested in finitary principles because independently of proof theory, they play an important role in mathematics. So having the ability to take an infinitary theorem and identify the finitary version that corresponds to it is really useful. And proof-theoretic techniques allow us to do that in a systematic way. And actually identifying the correct finitization of a theorem is not easy at all. Even for the simple monotone convergence principle, it's not obvious what this should be. And for more complicated theorems, actually having proof-theoretic techniques at your disposal makes this much easier to do. So that's one reason why we're interested in going from infinitary to finitary reasoning, and why it's really good to have proof-theoretic techniques that allow us to do this. But now I'm going to come back to what I talked about right at the beginning of the talk, which is another application of kind of converting infinitary principles to finitary principles. And that is that there are a lot of existential theorems which use infinitary principles as a lemma. Okay, and the example I gave right at the start used the Riemann hypothesis, so a case distinction on the Riemann hypothesis as a lemma to prove that something exists. In other words, there's a point at which this sequence changes for the first time, the sign alternates. All right, so we have a really horrible, complicated, non-constructive thing, and it's proving that a number exists. Something very, very simple. So these proofs are non-constructive, and we have no way of finding x if we can't do what we did to Euclid's proof. We have to do something more. We have to kind of actually transform the proof in some way. But there's a formal way of replacing the infinitary principle with its finitary counterpart, kind of plugging the finitary counterpart into the proof, and the result is then a bound on how far you need to look to find the very concrete thing that you proved existed. All right. So at the very beginning of the talk, I talked about proof-theoretic techniques in a very mysterious way, and how by kind of looking at an approximate Riemann hypothesis, we can get a bound on the first alternation. And then I gave some examples of some real concrete finitizations. So the Drinker's paradox and the finitary Drinker's paradox, finite convergence principle, the normal monotone convergence principle and the finite convergence principle. And I've tried to convince you that these are parts of a general, kind of both instances of a general logical technique. So this is the case, and proof-theoretic techniques allow us to transform infinitary principles into finitary ones, and then we can replace the infinitary lemmas that are used in the proof of something concrete with their finitary counterparts, and this way we can get a bound. So remember Kreisel, if it holds when the Riemann hypothesis is true, it should also hold when the Riemann hypothesis is nearly true. Okay, it's exactly this phenomenon. And this is something that where now there's a large amount of literature that tells you how to do this. It tells you in what circumstances you can do this, what kind of proofs are amenable to this kind of analysis. And there are there are now hundreds of examples where this kind of thing has been done. And a very concrete thing, a rate of convergence has been obtained by essentially this trick of looking at the infinitary lemmas involved in the proof and finitizing them. Okay, so now to bring these two things together, we have computational information from proofs. That's one thing that applied proof theory can do. And the other thing it can do is to give you finitary formulations of infinitary principles along with the relevant numerical data. And these two things are connected. The third thing it can do, and this is, I'm not going to talk about this in any level of detail because that's a separate talk in its own right, but it relates to what Clément said right at the start, which is that if you've kind of taken an infinitary thing and you said, well, actually, all we need is a finitary thing, you've strengthened the theorem in a quantitative way. You haven't just produced a bound on something or a rate of convergence, but you've actually said that the assumptions that you need to prove this theorem are weaker than what you thought. Okay, and so there are many, many cases where this can be done, and where the analysis of the proof not only gives you something quantitative, but it also weakens the assumption. It says that actually, looking carefully at this, I never needed that assumption in all its strength. And sometimes I never needed that assumption at all. So no need to understand this theorem. I'm just, again, putting it there so you see the shape of it. This is a logical meta theorem, which says it explains a phenomenon. So it says that there are lots of theorems which have a particular logical form. And one of the assumptions is that a fixed point set of an operator is non-empty. And it turns out that if you analyze under very general circumstances, you can always lose the assumption that the fixed point set is non-empty. So if you have a theorem that can be put into this logical shape, and one of its assumptions is then that a fixed point set is non-empty, and you can prove it in some sort of formal system, then there's a meta theorem that says that if you could do that, then actually your assumption that the fixed point set is non-empty was never needed. Okay, so that's the only thing I want to. I don't want to go into any of the details of this theorem. I just wanted to give you an example of a real thing where an assumption has been eliminated in a very systematic way. Okay, and that's the third thing that you can do with applied. I mean, these are three things that you can do with applied proof theory. There's more, but these are the ones I wanted to highlight in the beginning of this talk. Is that you can get logical meta theorems and abstract variants of proofs in the literature, which explain and generalize mathematical phenomena. And one of those interesting phenomena is when you look more closely at a proof, then assumptions can be weakened or even eliminated. Okay, so this is what we can achieve with applied proof theory. And I hope that I've given you a kind of a taste of the ideas and the techniques that are behind this. Of course, it's very high level, and you can't really say more than this in half an hour. But I hope by at least putting some of the theorems on the slides, I've given you an idea of what goes on.
I think you gave a really good idea, and you're right at 30 minutes. So.
Oh no,
the timing is perfect.
Wow. I'm really happy when that happens. It's completely unintentional. I could have talked for an hour. Okay, so an interesting question, of course, now that the proof theory can do this. What are we looking for if we want to bring these techniques to bear on a new area? So suppose you've played around in analysis, you've produced some theorems, and you ask, well, maybe this works in number theory, maybe this works in probability. Okay, there's lots of areas of mathematics where proof theory has never been applied in this way. So what are we looking for? And that's a very, very difficult question to answer. Okay, so finding a new case study for proof theoretic techniques in an area of maths where this has never been done before you can be proud of that when you've done it. But there are some very kind of general points that are worth looking for. So numerical information is relevant. That's something important, right? You want to be working in an area where if you produce a rate of convergence or a bound or something like that, then people are going to be happy about it. All right, so you have to be working in an area where numerical information makes sense and is relevant. Another important point is you want to be working in areas where there are lots of non-trivial proof, but the theorems have a nice structure from a proof theoretic perspective. So convergence is a great example of this. Convergence is a really simple theorem to state logically, but a lot of convergence proofs use really, really complicated machinery. So what you're looking for is syntactically simple proofs, syntactically simple theorems and very complicated proofs. So that kind of the syntactic simplicity of the theorems means that it's more likely that you're able to reformulate them in a meaningful way and get a finitary version that's relevant and interesting to the mathematicians. But the non-trivial proofs are what you need so that your proof theoretic techniques actually do something useful, so that people without proof, somebody could come along to the proof and just say, oh, well, it's obvious that's what the bound is. You don't want that to happen, right? You want to be in a situation where it's necessary to apply these techniques. And another thing you want to perhaps bear in mind is to find a situation where there's lots of variations of core ideas in different settings, because in those circumstances, often what you can do after thinking about things a bit and maybe writing a few papers is you can start to exploit this ability of proof theory to identify and to formulate general phenomena. And then you can start giving meta theorems and explaining on a higher level, using proof theoretic terminology, why something happens. Okay. All right. So now I want to quickly go over, again, in a very high level, some recent work I've been doing in applied proof theory. And this is in Tauberian theory. And it's just, this is very new, and it means that I haven't really thought about this in any great detail. So I'm still not sure how successful applied proof theory is going to be in this area. So I'm not presenting this as the next big thing in proof theory at all. It's just I'm just giving you some ideas, something that might work. But what I'm hoping to do is to at least get across the process of how, as a proof theorist, you might go about thinking about finding new areas to apply the techniques. Okay. So Tauberian theory grew out of a very nice theorem from elementary analysis, which is basically a converse to something called Abel's theorem. So I'm just going to put some facts from analysis on the slides. But even if you've never seen these before, I'm hoping that the sort of the connection with proof theory is going to make a bit of sense. So Abel's theorem relates two forms of convergence. It says that if I have a sequence of real numbers and I look at the power series that it generates, and then whenever that sequence of reals converges to some limit, then the power series converges to the same limit as x converges to 1 from below. So basically it relates two forms of convergence: the convergence of the coefficients of the power series and the convergence of the power series as a function towards its radius of convergence. Okay, so it's really useful because, you know, whenever you see these weird results in analysis where you know, some infinite sequence is log 2 and you wonder how was that proven, Abel's theorem is a good technique for doing this. It relates kind of a function to the infinite series generated by the coefficients. So it's a really useful technique. And so it's natural to ask, is the converse of Abel's theorem true? In other words, if I know something about the convergence of the power series, can I say something about the convergence of the series itself? And no, it's not true. So the counterexample is, for example, the function 1 divided by 1 plus x. So that's its power series. The function itself converges to a half as x goes to 1, but the alternating sequence of coefficients doesn't converge. All right, so at face value, Abel's theorem doesn't have a converse. And so Tauber's theorem is an attempt to fix Abel's theorem, an attempt to give it a converse and to produce an additional condition under which you get the converse. Okay, and this is something called the Tauberian condition. So without this condition here, without this, let me start properly. So Tauber's theorem says that suppose that I know something about the convergence of the power series. So I know that the power series converges to some limit as x approaches its radius of convergence, and I know something about the growth of the coefficients. So Tauber's original condition was that the size of the A of n is little o of 1 over n. If I know something about the growth, then I can prove that the coefficients converge to something. Okay, so it's basically the converse of Abel's theorem, but with an additional condition to make sure it works, because without that condition, it won't work in general. So this is proven in 1897 by Alfred Tauber, and apparently he was an expert in the mathematics of insurance, but he's now primarily known for this really nice theorem which bears his name. So that's Tauber's theorem, the first Tauberian theorem, and it has a nice shape. What it says is the following. It says, I look at a power series that's generated by some sequence of coefficients, and if I know something about the behavior of the power series as it as x goes to the radius of convergence, and I know something about the growth of the coefficients that generate the power series, then I can conclude something about the convergence of the coefficients. And this basic idea has been massively generalized now. So you can look at different ways of generating functions. So instead of the power series, you can look at an integral, and there are different kinds of growth conditions. So basically Tauberian theory is the area which looks at theorems of Tauberian kind, where you relate two different kinds of convergence and you throw in a growth condition. So I mean, I'm simplifying things massively, but that's what a Tauberian theorem is in a more general setting. And there's a whole textbook about this, which is over 500 pages. So it's and it starts with this initial theorem of Tauber, and it goes throughout the century. And there've been more and more and more results with increasingly sophisticated proofs. All right, so Tauberian theorems have a nice shape. It goes from convergence plus growth condition to convergence. And convergence is something that we already know from applied proof theory has a nice enough shape. It's amenable to analysis. So we look at proofs, can we get a rate of convergence? So a natural question is, can we give a quantitative interpretation of these theorems? So maybe going from a rate of convergence to some kind of quantitative growth condition to another rate of convergence. And in many cases, this would seem to pose a challenge because proofs of Tauberian theorems are often based on very complicated analytic techniques. Okay, so when I was first stumbled across this book and Tauberian theory, I thought this looks like something that might be amenable to proof-theoretic techniques, because it has all those things that I pointed out on at the end of my introduction. It's got it talks about something simple. It's convergence, right? The proofs are really complicated, and there's lots of them. So it has those sort of informal criteria that at least for me indicate that there might be potential for applying proof-theoretic techniques. So in the last bit of this talk, I'm going to mention some simple results in this area that I published. I'm going to present some unpublished work, and then I'm going to outline some rough ideas for the future, which is just speculation at this point. So here are the simple results. And so this is something I did, I think, last year. I was messing around with Tauberian theorems and to see what I wanted to analyze the very simple Tauberian theorems to start with, to see what would happen. So the first thing I did was give them a Cauchy variant. So rather than talking about the limit directly, I just talk about Cauchy convergence and Cauchy convergence. And one of the reasons why in applied proof theory you tend to talk about Cauchy convergence rather than normal convergence is that it simplifies the logical structure of the convergence theorem, rather than saying there exists a limit such that you can just say, well, my logical statement just talks about the sequence itself. Okay, so I reformulated them into Cauchy variants, and again, no need to understand this at all. I'm just putting it there so you see what it looks like. Remember that when I talked about the finitization of the monotone convergence principle, instead of convergence, we had blocks of finite convergence. So basically blocks where the elements of the sequence were within epsilon of each other for a finite space. And so, you know, we're going from convergence plus growth condition to convergence. And so one thing you can potentially do is see if you can go from finitary convergence plus something to finitary convergence. And that's one of the theorems I produced, which, I mean, it looks much more complicated than it is. It just says that if in the conclusion of Abel's theorem, I want to establish not convergence, but finitary convergence, it gives you exactly how much finitary convergence you need in the premise of the theorem. And from that, you can actually get a direct rate of convergence in the case that you have a rate of convergence for the input. Okay, so remember, Abel's theorem says that if I know that the coefficients converge, then I also know that the function converges. And by looking at the proof, you can take a rate. If you have a rate of convergence for the coefficients, then you can produce a rate of convergence for the function.
Can I ask you something?
Yep.
I'm sorry, I didn't mean to interrupt. Was it the first time that there was a Cauchy sequence variation on the Abel theorem, or did you know that any other Cauchy interpretation of that theorem?
I couldn't find any, but that's not to say that it didn't exist. I didn't look very hard, and also it doesn't take anything deep to formulate these. So as far as I'm aware, that I didn't see them, but there's no reason why they wouldn't exist. If they didn't exist, it's just because nobody cared about them. So there's nothing impressive about these, and showing that these are equivalent to the original ones are just kind of a short exercise.
Well, I mean,
yeah, but I also asked myself
some intuition and some imagination to apply those techniques to that theorem. So, okay.
Yeah, I also asked myself whether this existed somewhere. I don't know.
Okay, thank you.
So yeah, and I should say that the proof of Abel's theorem and Tauber's original theorem, these are elementary. Okay, so there's no analytic number theory involved. It's just elementary manipulation of series. But if you look at them closely, then you can take a rate of convergence for the sequence of coefficients and produce a rate of convergence for the function formulated in a Cauchy setting. Okay, and it looks fairly simple. And I can do exactly the same thing for the other direction for Tauber's theorem, which is the real thing I want to talk about. Again, I mean, it's the same basic idea. I'm not going to go through the numbers. I'm just putting this up so you can see what the complex version looks like, and the simple version is this. So I have a rate of convergence for the function, because remember, Tauber's theorem goes from the function convergence to the coefficient convergence. So I've got a rate of convergence for the function, but I also need a rate of convergence for the coefficient for this to represent this growth condition. So I need a numerical version of the growth condition as well. And if I have those two things, then I get a rate of convergence for the coefficients. Okay, and again, it's a very simple like polynomial function. And again, there's nothing very deep in this. Okay, I just looked at the proof. I kind of carefully I formulated the theorems in their Cauchy variants. I went through the proof in carefully and kind of unwound the quantitative information that was implicit in the proof, and the result is that. And I wrote this up in a short paper, which has been published in Mathematical Logic Quarterly, and that's what it's called, a note on the finitization of abelian and Tauberian theorems. And you can see right at the start, I talk about metastability, because it's a nice way of motivating this, going from convergence to convergence, and you want to go from rate of convergence to rate of convergence, or metastable convergence to metastable convergence. Okay, and that's available on my webpage if anyone's interested. But the only reason I did this was because I wanted to use it as a stepping stone for more interesting things. Okay, so these results on their own, there's really nothing deep in this. It's just taking some elementary proofs from analysis and applying stuff I knew from proof theory to get some simple rates of convergence. But that's all there is to it. What I'm really interested in is looking at some of the more complicated Tauberian theorems. Okay, so Tauber's original theorem was, like I said, the proof it's a really nice theorem, it's a really nice proof, but it's very elementary. So back at the beginning of the 20th century, Littlewood, the British mathematician, was looking at these, and he noticed that Tauber's growth condition was not optimal. So there are many sequences which didn't satisfy, which were much more general. So they had a more general growth condition, but they still they were still convergent. So it seems that Tauber's theorem can be strengthened. So he noticed this, and he gave a strengthening of Tauber's theorem, which corresponds to a weakening of the Tauberian condition. So what Littlewood showed is that, so this is exactly Tauber's theorem. The only difference is that rather than asking that the NAN converge, it suffices to have an upper bound on these. So it's a very small cosmetic change to Tauber's theorem, a weakening of the Tauberian condition. But the original proof was deep and required lots of analytic number theory. Okay, so a small weakening in the assumption of this Tauberian theorem and a strengthening of the Tauberian theorem resulted in a very different kind of proof. And in a mathematical education, Littlewood writes, on looking back, this time seems to me to mark my arrival at a reasonably assured judgment and taste, the end of my education. I soon began my 35-year collaboration with Hardy. So for him, this was also something that he, from what he writes, perhaps was proud of, or perhaps felt that this was something significant. So, and I include that just to, again, emphasize that this is a very different kind of proof. It's not a simple proof anymore. It's something deep. And again, there's this phenomenon where when you look at the theorem, it's a very, very small change, but the proof is much more complex. And indeed, he went on, and one of the first papers he wrote in this famous collaboration with Hardy was yet another strengthening of Tauber's theorem. And I'm just going to put that up here now. It's formulated slightly differently now. And I don't want to talk about this in detail. This is the Hardy-Littlewood Tauberian theorem, but you can use this to give a new proof of the prime number theorem. So, and the only reason I mentioned that is to show just how deep this is now. This is no longer a simple result about infinite series, but it's something subtle enough that you can basically use it to prove the prime number theorem. And that also shows you that we're no longer in the realm of elementary analysis, but we've gone into kind of analytic techniques. Okay. So for this reason, I was interested in Tauberian theorems, because they very rapidly go from elementary proofs to very subtle proofs, but the theorems stay pretty much the same. Okay, so if you can reformulate the theorems in a way that kind of makes sense from a quantitative point of view, then that stays the same, even when you're looking at the more complicated Tauberian theorems, but the proofs are much more complicated and much more fun to analyze. And that's what I've been doing recently. So this is unpublished, and this is a finite Littlewood theorem. So I looked at this theorem, and tried to extract some kind of rate of convergence from it, a general rate of convergence for this Tauberian theorem. And it's not quite as simple as what I showed you before. So you need to appeal to quantitative results about kind of the degree and coefficients of approximating polynomials. So you need to actually appeal to some results in numerical analysis to get these bounds out. So it's no longer a case of kind of following the proof and just kind of unwinding the little bits of numerical information in the way that we did for, say, Euclid's proof that there are infinitely many primes. This requires some kind of, it requires you to look in textbooks and check what these numerical bounds are and then apply them. And similarly, one can get a direct rate of convergence. It's an instance of this. So if you have a rate of convergence for the function and a bound for the coefficients, then one can produce a rate of Cauchy convergence for the infinite series. Okay, and you get all this from just analyzing the proof and using numerical results when they're needed. Okay. And what I liked about this, so one thing you want to do when you're looking at, when you're applying these techniques from proof theory is you want to ask, how are my bounds compared to those that a mathematician has produced? The first question is, has anyone else been looking at bounds in this area? And if so, what are they like? Because if no one's been looking for bounds in that area, that suggests that nobody cares. And that's potentially not a good place to apply proof theory. And if they have been looking at bounds, if everyone's busy looking for bounds and there's a huge effort and they're much, much nicer than the ones that you got using your proof theoretic tools, then that's also not a good reason to do it, right? Because you're just producing worse bounds using more complicated techniques. So what you want is you want to be in an area where people care about the bounds, but somehow the proof theoretic techniques seem to be on a par or better to what the mathematicians are doing. And so I found an old paper from the 1950s, and this is written by the same person who wrote that big yellow book. And this was about the remainder in Littlewood's theorem. Remember, the remainder is effectively the rate of convergence. Okay, and so this is a paper where he looks at approximation, so L1 approximations. This is the approximation of continuous functions from polynomials, and he used that to get essentially a bound on the rate of convergence of the series by looking at the proof of Littlewood's theorem. And there is an example here where he says, well, if the power series converges, so this is 1.6 here, if the power series converges to its limit at this linear rate, then the sequence of coefficients converges to the same limit at inverse logarithmic rate. So those are the sort of rates of convergence that you're getting. So it's very clearly analogous to kind of what you would be doing with applied proof theory, going from a rate of convergence to a rate of convergence. And I was quite happy that by reformulating everything in terms of the epsilon delta moduli of continuity that we use in proof theory, the result was similar. So what I have at the moment is a sort of quite a general quantitative version of Littlewood's theorem, which in this particular instance matches up with one of the old papers from the 50s where remainder theorems were produced. So what this shows is that the analysis that you're doing with kind of proof theoretic ideas is in line with what mathematicians are doing, and it shows that potentially there's something to be said here. Okay, so potentially when you go then to give an abstract version of this, a more general version, and you can say, well, in this case, it matches up to known bounds, then it's meaningful, right? Nobody wants you to give a bound that's massively inefficient or way more complicated than those that exist in the literature. But if you can show that it does match up to those ones that are known in simple cases, then maybe people care about it. So again, I haven't done a huge amount of, this is all very preliminary, so I haven't done an extensive search of the literature. It could be that in the last decade, somebody came up with a much better bound. It could be that these bounds are not optimal. So I don't know, but kind of initial work in this direction has shown this to be promising. And it's promising enough that I'm interested in looking at it further. Okay, and that brings me to the end of the talk. So at the beginning, I gave this exactly 30-minute introduction to applied proof theory. And then I showed you something that I've been doing recently. So I did a very simple quantitative analysis of the original Albe and Tauber's theorems. It's not deep, but it's maybe useful and a nice example of finitization. I don't know. And what I'm looking at now is a quantitative analysis of the Littlewood. So, I mean, what I've done is an analysis of the Littlewood-Tauberian theorem. And of course, the next question is, where does it go from here? So open questions. Can we finitize the Hardy-Littlewood theorem, which is yet another level of difficulty? And what about deeper results in Tauberian theory? So those involving integrals, for example. Can we produce new remainder theorems which don't have any precedent in the literature? Are there instances where in Tauberian theory there are no remainder theorems yet, and the proof theoretic analysis gives you something for the first time? And then finally, are there these abstract meta theorems which could maybe generalize certain phenomena that appear in Tauberian theory? So this is pure conjecture. Okay, I'm not claiming that any of these questions has a positive answer, but I think they're interesting, and I'd be really excited to know what's possible here along these lines. And that's everything I wanted to say.
Okay, thank you, Thomas. Thank you so much for this interesting talk on type proof theory. So the floor is now open for questions, I guess. You can type them in the chat or raise your hand or just wave at the camera.
I haven't been looking at the chat.
I just put the links to the various paper and blog posts you mentioned. I'm actually interested in the Thierry Tarot one. I think I have a
it's a really nice essay.
Sorry, I have a question. First of all, Thomas, thank you very, very much. That was an excellent talk.
Thank you.
I have a couple of remarks first, more historical remarks, because I'm an old guy. One is that you may have seen an article by Eric Bishop called Mathematics as a Numerical Language. And it occurs in an ancient book by Kino, Myhill, and Vesley on intuitionism and proof theory. And in there, he advocates for the use of Gödel's dialectica interpretation for getting numerical results as a formal method. Yeah. And another thing that reminded me, the one and only time I can remember when I was a graduate student, I saw Kreisel give a talk, and he talked about a historical theorem, which kind of was interesting about towards the end here, your interesting remarks was, he said there was a theorem, I think of Davenport in number theory, and then, Roth in number theory. And then later Davenport gave proof with some bounds. And all the number theorists at the time were just saying, something fishy about this. It's not great mathematics. And then Kreisel realized that in fact the second theorem arose from Roth's original theorem by just using Herbrand's theorem. Yeah. So it was just pure logic. Yeah. And that's why the mathematicians dismissed it, kind of. It's just logic. And then it was later, though, that Kirby, I think his name was, the number theorist, got a Fields Medal for really increasing the bounds using fancy mathematics. And so there was always this kind of feeling that, well, that's just logic, you know.
Yeah, indeed, it's these results of Kreisel, just the idea of using logic to obtain these bounds is extremely impressive, because at the time there was nothing like that, right? I mean, at the time these techniques were tools for proving relative consistency, and so the idea of turning them on their head and actually using them for something positive was really radical. So it's very impressive, and somehow it's only now that the kind of the fruits of these ideas are really being established in mathematics, and the mathematicians are accepting them and saying, well, this is interesting, and we're going to publish this in our journal. So the idea of turning them on their head and actually using them for something positive was really radical. So it's
I guess you spoke of dialectic interpretation.
It's only
but
now
you could also speak of no counterexample interpretation. In
the fruits of these ideas are
really do you see a difference there? Kreisel were making a lot of this distinction, but maybe it's not so important.
So the no counterexample it coincides with the dialectica interpretation for formulae of a particular shape. So simple for all exists for all theorems. And then it diverges for more complex theorems. And what you lose so the dialectica interpretation introduces higher types, whereas the no counterexample interpretation stays at type 2. And what you pay for staying at type 2 is that you don't have modularity. And there's a paper by Ulrich Kohlenbach which proves this. So the no counterexample, if you've got a no counterexample interpretation of A and a no counterexample interpretation of A implies B, you can't necessarily put those together to get a no counterexample interpretation for B, but you can do that if you use the dialectica, because the higher types allow you you gain modularity that way. Staying at type 2.
But in your experience, you use dialectica essentially.
So the no counterexample, if you've got no counterexample interpretation of A. Yeah, so I mean, I say we use dialectica. It's not like you apply. You use it sometimes. You use it to. If there's a bit of the proof that you find tricky, or you're not sure how to correctly give the finite form of that particular lemma that you've seen, the dialectical interpretation somehow tells you how to do that. So you use it as a guide, but you don't use it kind of in a brute force way. I mean, I say we use
Thank you.
dialectica. It's sure. Not like you apply. You use it.
All right, thank you so much. I have maybe another comment about using dialectica or other tool from proof theory. We had an interesting talk by Tarmo Ustalu, I think 2 or 3 weeks ago, who actually proved a new result on skew X categories using focusing in proof theory. So I thought, I just mentioned that. I thought it was an interesting thing too, to see that focusing was allowing him to actually construct a relatively small proof theory system that allowed him to show new results on skew X category. So I didn't expect your two talk to connect in this way, but I think that was interesting.
Okay. No, I'm not familiar with this work.
Okay, so I think it's another point of comparison or of introduction maybe to applied proof theory. So maybe I can give you a pointer later.
Yeah, that would be really good. Thank you.
Okay, I will. And maybe just out of curiosity, you said that the bound you derived was similar, so the one inverse of log was similar to what you found in the literature. So how close is it? And also, I think it's kind of tempting to cheat a bit and use pre-existing results as a guide and say, okay, they get that, so can I do better? Or can I, like, what did they do so that I can get closer to what they have? No,
that's true. You definitely cheat. You definitely see that in advance that there are sort of numerical bounds there, and you know, it looks roughly the same. I haven't done a closer analysis. It's simply there as a sanity check to make sure that in the initial case studies that you're looking at, that the proof theoretic analysis is in some sense clean and efficient and not introducing. It's not the case that there are, what you want to avoid is that there are a load of brand new proofs that are very different and give you very efficient numerical bounds, because then you're never going to compete with them. But it's interesting, the question of which proof do you analyze? What proof is good from a proof theoretic point of view? And it's often the case that old-fashioned proofs are better because they're more quantitative. So modern mathematicians use modern methods, which are very non-constructive, and old-fashioned mathematicians from the 19th century use very explicit methods. And so often that's the best proof to look at if you want to try to get some sort of numerical information from it. So it's a nice example where the old-fashioned proof is still useful and relevant if you're looking at proofs from this point of view.
Okay, so is there any other question for Thomas? I think that's it. Okay, so feel free to stay. So I'm gonna stop the recording, but feel free to stay in the Zoom meeting if you want to have a chat with Thomas. In any case, thank you so much, Thomas, for accepting our invitation and for this really great talk. Bye-bye.
Thank you.